Hello everyone and welcome back to Teach Astronomy. How you guys all doing today? Sorry, there's something distracting on my other screen. Hope everyone's doing well this Monday morning. Excited for the final chapter of Einstein's Monsters. I see some people are already in the chat. It took me a minute to get started today because I totally forgot to put the images from the last chapter into the PowerPoint so I can show you guys. Since we learned a long time ago that my camera does not focus on anything closer than like a foot away from it. So hopefully I'm far enough away where I'm in focus. But yeah, so today we're going to be reading the last chapter of Professor Impey's book, Einstein's Monsters. If you haven't been here before, we've been reading this for like 2 months or so. We started it in November, but we took a couple breaks because of, the holidays and Martin Luther King Day last week and stuff. But we are at the very end of it. So today we're going to be finishing it. And then next week we will have a Q&A with Professor Impey, either at this time or at like 11 a.m. Pacific Standard Time, which is like an hour from now. Because we have to figure out what his schedule is. But we'll be able to ask him a bunch of questions about the writing of the book and black hole stuff and cool things like that. So let's just finish it on up today, I guess. Oh, it's okay if you missed it. So actually the entire thing is archived on YouTube. So, and it's like, it goes in a kind of order. But it is a nonfiction book. It's not like there's going to be like spoilers at the end, like, oh gosh, they discovered black holes. I wasn't supposed to know that until chapter 5, or, it's fine. But, if you guys want to stick around, I would love if you stuck around today. But if you want to go back and listen to the other ones, we have them all archived on the Teach Astronomy channel. And I can link that really quick before I start. But yeah, we also just like hang out and like chit chat and have a good time. So sorry, I managed too many YouTube channels and I'm trying to find the right one. Okay, here we go. So that is where they're all archived. That's the Teach Astronomy channel where we have all of Chris's courses. It's different than the Astronomy State of the Art if you go to his live streams on YouTube. But yeah, so I guess we will jump on into it. Hello, Alexandra. How you doing? And yeah, so chapter 8 is called The Fate of Black Holes. Also, let me know if I'm too quiet or too loud or anything. I always ask with this mic because, hi, Lynn Jersey, how you doing? All right, so the fate of black holes. Can't hear myself. There we go. The future of black holes is a story of short-term growth and long-term evaporation. Our distant descendants might witness the center of our own galaxy flaring up as a quasar, and the merger of the supermassive black holes in our galaxy and Andromeda. Eventually, black holes will reach a maximum size and no new black holes will be created. Life could persist in the universe even in the future era of darkness, but it would be severely challenged by the final victory of forces of dissipation and decay. In the present, however, black holes present the ultimate test for any theory of gravity. The quest to reconcile the quantum theory with general relativity has led to gravity in multidimensional space-time. The 3 familiar dimensions of space only give hints of additional hidden dimensions. Black holes must be incorporated into this new framework. That's the little intro section. Hi, Barbara. Barbara 555. 5 5s. That's fun. I like that. That's a good time. All right. So next section is the new age of gravity. Why is gravity so weak? This doesn't seem like a sensible question, especially on a day when you find it hard to get out of bed. I feel that. Until, that is, you recall that a small bar magnet can hold up a paperclip against the downward pulling gravity of the entire Earth. Gravity is vastly weaker than the other 3 fundamental forces. Trying to explain this simple fact takes us down a rabbit hole of hidden dimensions and multiple universes. As we've seen, physicists already have clues that the four fundamental forces may be manifested as a single superforce at sufficiently high temperatures or energies. The unification of two of the four forces was seen at accelerators in the 1970s, resulting in the award of a slew of Nobel Prizes. Pursuing this path led to the idea of supersymmetry. In the everyday world, particles with half-integer spins, such as electrons and quarks, as a class called fermions, don't interact with particles with integer spins that carry forces, such as photons and gluons, as a class called bosons. For subatomic particles, spin is an esoteric mathematical property not directly analogous to the spinning of a top or a planet. Fermions and bosons are as aloof as oil and water. Supersymmetry unifies these categories by presenting a set of I am stumbling over my words today. It's early. Okay. Supersymmetry unifies these categories by predicting a set of shadow particles for every fermion and boson, and it predicts that all the forces except gravity merge into one force at the phenomenal temperature of 10 to the 29 Kelvin. Theorists reached for supersymmetry to pursue their dream of unity underlying the plethora of different subatomic particles. But supersymmetry has been questioned, because no hint of these shadow particles has been seen with the Large Hadron Collider. A second attack on unification emerged in the 1980s with string theory. String theory finesses the problems of the standard model of particle physics by hypothesizing that particles aren't fundamental, but are oscillation modes of tiny one-dimensional entities called strings. Excitement about string theory spread like wildfire through the theoretical physics community. The theory was based on very elegant mathematics, and it naturally united gravity with the other three forces. However, after more than a decade of intense research, many physicists grew discouraged with string theory. The mathematics was difficult and often intractable, and it required space-time to have 9 dimensions, which seems like 5 too many. In string theory, the hidden dimensions are only realized at the incredibly high temperature of 10 to the 32 Kelvin, or at the incredibly small scale of 10 to the negative 35 meters. It looked as if the theory was untestable. Enter Lisa Randall. Growing up, she was drawn to math because it provided definitive answers. She was the first female captain of her school's math team and a classmate of noted string theorist Brian Greene at Stuyvesant High School in New York. As an 18-year-old, she won the Westinghouse Talent Search Contest with a project about Gaussian integers. After getting her PhD at Harvard, she moved across the river to MIT as an assistant professor and became a rising star of theoretical physics. Lisa Randall has a muse for music as well as math. There's not much opera inspired by theoretical physics. Even an opera buff might scratch his or her head, perhaps coming up with Philip Glass's Einstein on the Beach. Lisa Randall has added to this small over with Hypermusic Prologue, a projective opera in 7 planes. Spanish composer Hector Pera wrote the score, and Randall wrote the libretto? I'm assuming that's the lyrics. I don't know much about opera. Also, hi, Astra Kiriani, welcome. If anybody knows about opera, let me know if the libretto is the music or is the lyrics, because that's my best guess. To see why Lisa Randall was inspired to think creatively about gravity, let's return to the knotty problem of singularities. According to general relativity, every black hole contains a singularity, a place where the curvature of space-time is infinite. Inside a black hole, Einstein's equations fall flat on their face and predict something physically nonsensical. Stephen Hawking showed that singularities are inevitable in a black hole, and he framed this problem dramatically. General relativity contains the seeds of its own destruction. One possible path through this impasse involves string theory. String theory is motivated by a number of issues in fundamental physics. One is to unify the forces of nature in one framework. The smooth theory of curved spacetime isn't consistent with the grainy theory of subatomic particles. This is the quest for quantum gravity that frustrated Einstein for decades. Also, the generally successful standard model of particle physics is flawed. Electrons have zero size in the model, so therefore must have infinite mass density and infinite charge density. Another example of singularity seeming to violate physics. There's currently no explanation for why there are so many fundamental particles with different masses, or why matter is dominant over antimatter, or why dark matter and dark energy are the two major constituents of the universe. Randall knew that research on string theory in the 1990s had explored the richness of branes. Brane, B-R-A-N-E, is an abbreviation for a membrane, a lower dimensional object in higher dimensional space. Think of a sheet of paper, which is a two-dimensional object within three-dimensional space. Ants crawling on the sheet of paper are confined to move in 2 dimensions. They're unaware of the third dimension. There might even be another sheet of paper with ants crawling on it, and those ants would be unaware of the parallel universe, quote-unquote, not far away from them in a third dimension. Analogously, our own universe might be a brane, an island of 3 dimensions floating in a sea of higher dimensions. Particles are confined to the brane, but Randall knew that gravity wouldn't be confined to the brane because general relativity says it has to exist in the full geometry of space. She realized this might explain why gravity is so weak. I'm going to pause there for just a second because this section's really long. Anyone here know about the Mond theory? I do not. I can look it up though. Let's find out. Let's see. What do we find? Modified Newtonian dynamics. Let's see. Modified Newtonian dynamics is a hypothesis that proposes a modification of Newton's laws to account for observed properties of galaxies. It is an alternative to the hypothesis of dark matter in terms of explaining why galaxies do not appear to obey the current understood laws of physics. Interesting. I don't know much about it. Clearly, I had to look it up to find out what it was. It sounds very interesting, though. Definitely something to ask Professor Impey about someday. Also, yeah, if you guys have questions that you've had either earlier in these chapters or that you're thinking of now, and you want to start throwing them into the chat, questions that I'll ask Professor Impey, that would be awesome. Because I don't know how many, there's a good chance that a lot more people will come to next week's because Professor Impey's going to be here and may ask a bunch of questions that, when can you ask him? About the Mond theory, you could ask him during his live sessions. He does live sessions every week, but we alternate whether it's on Twitch or YouTube. I think this week's is Twitch. I just haven't gotten... He'll probably tell me sometime today because his schedule changes so much week to week that he has to tell me on Mondays so I can schedule it. But yeah, he does live Q&A sessions, and he's super smart. If you're new to the channel, Professor Impey has got just a crazy resume. But he works at the University of Arizona now, and he is the smartest person I think I've ever met. So you could ask him like about anything there. But yeah, if you guys want to throw in some questions, so you make sure that there are things that I'll ask him next week, and we do not get bombarded by new people, feel free to put those in the chat. Also, if you guys just want to chat, how's the weather like where you guys are today? It's cold here. I say cold. I live in Los Angeles. It's like 50 degrees, and that's too much for me now, apparently. I heard it snowed in Tucson very lightly, which is crazy. That doesn't happen. But I hope the weather is nice by you guys. And I will continue. Randall had resisted the idea of extra dimensions for years. But at MIT, she collaborated with Raman Sundram of Boston University to brainstorm about branes. The math they came up with described a pair of universes, 4-dimensional branes, thinly separated by 5-dimensional space. They found that the space between branes was warped, and the warping could magnify and demagnify objects or forces between the branes. Therefore, Gravity can be as strong as the other forces on one brane, but if we happen to be on the other brane, we experience gravity as extremely weak. Randall and Sundrum were then stunned by another realization. That fifth dimension could be infinite, and we'd be unaware of it. Until then, physicists assumed the conventional wisdom of string theory, that the extra dimensions are coiled up so tightly that no experiment could probe them. In Randall and Sundrum's theory, they might be observable with accelerators. And we have a figure to go with that section. You heard it snowed in Malibu. I heard it had snowed somewhere. It might have been Malibu. That'd be wild. There it is. Okay. So here is a figure. So it says, one possible explanation for the weakness of the gravity force involves branes or membranes, lower dimensional objects embedded in a higher dimensional space. Gravity might be strong on one brane but weak on another brane, both being three-dimensional spaces embedded in a five-dimensional space. It's not yet clear whether or not the higher dimensions or neighboring branes might be detectable in a lab or accelerator. So, it's just a very basic figure showing that there's one brane where it's there's very high gravity, and the other brane where there's very low gravity. These are essentially supposed to be like these would be like two parallel universes essentially. And there's a graviton probability function about how many gravitons there are. I think that's just the strength of gravity. I think a graviton is like supposed to be like a gravity particle? I don't know if that exists. But it's the strength of gravity. It's higher in one and it's lower in the other. That's the whole thing. All right. This work made them superstars. Sundrum got 7 job offers. Oh, I wish I got 7 job offers. He mused about this good fortune, given how anxious he had been about their ideas. Quote, working that out was mind-blowing. We had reason to be dead scared. In each of these cases, there was a distinct fear of making complete fools of ourselves. Randall became the first tenured professor of theoretical physics in the long history of Harvard University. She ventured into writing popular books and, less comfortably, had been regularly called on to speak for women in science. Quote, I like to solve simple problems like extra dimensions in space, she noted wryly. Everyone thinks women in science is a simpler issue, but it is so much more complicated. We have a Women in Science series on Active Galactic. You should check it out. Branes are highly relevant for black holes. As we saw in Chapter 1, Strominger and Vafa used string theory to reproduce the black hole entropy and radiation that Stephen Hawking derived using classical physics. By wrapping branes around tightly curled regions of spacetime, theorists showed that they could calculate the mass and electric charge of the interior black hole. The fact that pure mathematics, developed for a completely different reason, can be used to calculate the properties of real objects like black holes was considered a triumph for string theory. For spring theory. We could be living in a bubble of 3 dimensions, floating in a sea of membranes of 5, 6, 7, or more dimensions. All of these commingle in a construct called the multiverse. This is distinct from the multiverse described at the end of the last chapter, which is based on other spacetimes that may have emerged from quantum vacuum states existing alongside the Big Bang. The string theory multiverse is a set of shadowy multidimensional spaces that coexist with the universe we live in. Higher dimensions haven't been detected yet in the laboratory or with accelerators. Many physicists think that branes, like strings, are clever mathematical constructs with little relation to reality. In some quarters, healthy skepticism has turned into a backlash. Yet Randall remains hopeful. The guru of gravity continues her work on the wild shores of higher mathematics. Let's leave the last word to a poet rather than a physicist, E. Cummings. Quote, listen, there's a hell of a good universe next door. Let's go. That's the end of that section. Also, while reading that section, I realized I totally forgot to let the Discord group know that we were going live. So I'm going to do that really quickly. Apologies to the Discord group and to you guys who are going to watch me waffle for a minute. What can we talk about while I do this? How's life? I hope everyone's doing well. Sorry. You guys can start. I didn't mention it before. I'm trying to type and also talk, and it's a hard thing. We are going to be voting on what book to read next at the end of this stream. So make sure you stick around, or if you have to leave, if you put your vote in early, I'll count it. But we're going to do a little poll. It'll be fun. Hey, everyone. We're the last chapter. Sorry, guys. It was one of those very hectic mornings, you know? And by hectic, I mean I woke up really late. Yes, I want to mention everyone. Okay, is that gonna... Did I type the link wrong? I didn't. Okay, good. Have I read any of Stephen Hawking's books? I have not. I need to. I want to. I usually actually gravitate towards more, like for my own reading, I gravitate towards a lot of fiction, especially like fantasy and sci-fi stuff. But I want to read more outside of Professor Impey's books. But yeah, I read, I think it's called Welcome to the Universe by like Neil deGrasse Tyson and two other people whom I'm forgetting. I liked that one a lot. But yeah, I gotta switch it up a little more. I'm like, I'm not in like college anymore, and I'm like, maybe I can continue to educate myself with some nonfiction. Yeah, because I like nonfiction. I just don't read a lot of it. Okay, we're going to continue now that that has been handled. Apologies for the delay, by the way. Anyone watching this back on YouTube, I'm so sorry. And we are going to go to the next section, which is called Quasar on Our Doorstep. Black holes are evolutionary dead ends. For a massive star, they represent the outcome where no energy can be generated, and gravity is the victor. Supermassive black holes at the centers of galaxies are the deepest gravitational pits in the cosmos. They'll grow inexorably, and they can't be starved forever. We have a ringside seat for the evolution of the nearest massive black hole, the one in our own galaxy. Is it possible to look back to a time when the Milky Way flared into life, to predict a time when it might burn brightly in the future? The best probe of activity is the X-ray emission, since it can reach us through the gas and dust of the galaxy's disk, whereas optical light is extinguished. In the 20 years that X-ray telescopes have been monitoring Sagittarius A*, it has mostly been very quiet. There are flares every few months that brighten it by a factor of 5 to 10 for less than an hour. But that's just 20 years of observation. It's possible to see changes in black hole fueling on timescales longer than a human life. Data combined from 4 different satellites detected the X-ray echo of a big flare from 300 years ago. At that time, Sagittarius A* brightened by a factor of 1,000,000. Then the radiation reflected off a molecular cloud several hundred light years from the black hole before arriving at the Earth. The initial radiation mostly reached Earth in the early 18th century, when no one had X-ray telescopes to observe it. The event itself occurred 27,000 years ago, when our early ancestors first reached northern Asia after leaving Africa for the first time. An event this bright probably involved the black hole ingesting a star. Oh, thank you for the follow. Why was that so quiet? My alert box is very low. There we go. We're going to turn that up a little bit. Thank you so much for the follow. Welcome to the TeachAstronomy family. What about even longer timescales? Can we see what the currently slumbering black hole in the center of our galaxy was doing millions of years ago? Yes, and doing so solves a puzzle associated with the mass budget of the Milky Way. Our galaxy weighs 1 trillion times as much as the Sun. About 85% of that is dark matter, the invisible and mysterious substance that holds all galaxies together. That leaves about 150 billion solar masses of normal matter. Unfortunately, when astronomers added up all the stars, gas, and dust they could see, it was half that amount. They found the missing matter with an X-ray telescope, in the form of hot, dense fog permeating the galaxy. They saw a low-density bubble extending from the galactic center 2/3 of the way out to the Earth. They calculated the energy needed to evacuate such a large bubble and deduced that the Milky Way must have had a quasar phase in the past. The shock wave is moving at a speed of 2 million miles per hour, and it will reach us in about 3 million years, so there's no reason to panic. Tracing it back across 20,000 light years implies that the quasar phase started 6 million years ago, when early hominids walked the Earth. The timeline is corroborated by the presence of 6 million-year-old stars near the galactic center, which probably formed from material that flowed toward the black hole during an even earlier feeding phase. The Milky Way black hole went on a feeding frenzy 6 million years ago, then belched out so much energy and gas that it ran out of food and went into hibernation. What does the future hold for the galactic center? It's in a very quiet state now, but that won't last forever. We can expect the quasar on our doorstep to ignite every few 100 million years. There are signs that the galactic center is gathering itself for another active phase. X-ray observations have provided evidence for a swarm of 20,000 black holes and neutron stars within 3 light years of Sagittarius A star. This is the highest concentration of collapsed stellar remnants anywhere in the galaxy. They migrated to the center over a period of several billion years. If you have a bowl containing black marbles and wooden balls the same size and you shake it, the marbles will migrate to the bottom of the bowl because they're heavier. Similarly, gravitational interactions will cause black holes to be more centrally concentrated than the much larger number of normal stars. Still, the odds are extremely low that we'll witness a return of quasar activity. For a galaxy like the Milky Way, the black hole is likely to brighten by a factor of 1 billion during only 1% of the remaining 5 billion year lifetime of the Sun. The last time the Milky Way was a quasar was when chimps and humans diverged on the evolutionary tree. The next time might be tens of millions of years in the future. If we were still around as a species, what would we see? Nothing obvious. There's so much dust between us and Sagittarius A star that most visible light would be blocked. Radio jets invisible to the human eye would bisect the sky at right angles to the Milky Way. High energy radiation would also surge, causing elevated mutation rates. Unless we took permanent shelter, our DNA would be steadily shredded. But if we could rise 100 light years out of the galaxy disk, from that perspective, we'd have a majestic view onto the flaring black hole, its accretion disk shining as bright as a full moon. And that's the end of that section. Gotta move that. There we go. Welcome, CJ SideQuest. I realized I didn't say your name before. Thank you for the follow. What do you guys think? I was reading that section and I was like, well, maybe if we were still around as a species, maybe we would have evolved to have, I don't know why this would happen, but maybe we would have evolved to have to be able to see in different electromagnetic wavelengths. Maybe we could see radio waves. That'd be wild. What do you think would be the coolest evolutionary ability we could get in the far future? It doesn't have to be realistic. You could say we could fly or something. I would like that. I would like to hear what you guys think, though. I would love to see in different wavelengths. That would be sick. You know, because you see these pictures of the radio wave galaxies and stuff like that, and they look so cool. And I just want to look up into the sky and see that we could fly. I don't know where the wings would come from. It would take a long time, right? But Would that be necessary? Probably not. Would it be fun? Hell yeah. Telepathy would be wild. Photosynthesis. Flying to other worlds. You mean like physically flying? Wormholes. We could... I like these options. I'm just trying to imagine how these things would happen. Like telepathy, how does that evolve? It'd be wild, right? Because that's like a echolocation. I've heard some people, okay, this is like, I don't know too much about this, but there are some blind people that are able to kind of mimic the like echolocation sort of thing that like I think dolphins do. No, not dolphins. Porpoises or something do. And they can like they have a lot of blind people use canes, and if they tap their cane, they can kind of tell, they can train their ear based on the way that things reflect, like where edges of a room are and stuff like that. And that's just cool, I thought. I do not know how snakes actually see things. Please educate me. I know there are some species of animals that see like shrimp see like a bunch of other colors than we do, which is crazy. I'll look that up. You explain to me how snakes see. I'm going to start reading the next section. We will come back to the snakes, and then we will come back to the shrimp, because now I'm curious. Okay, merging with Andromeda. We're on a collision course with our nearest neighbor. Before the sun dies, the Milky Way and Andromeda will approach, interact, and merge, with uncertain consequences for the solar system and its inhabitants. The merger of the black holes at the center of each galaxy will be one of the most spectacular events imaginable. We've known for a century that M31, the Andromeda Galaxy, is approaching us at a speed of 120 kilometers per second, or 270,000 miles per hour. Galaxies are generally receding from us due to the expansion of the universe, but the Milky Way and Andromeda are close enough that their mutual gravity overcomes the cosmic expansion. Hubble Space Telescope measurements of the sideways motion of Andromeda reveal that it's heading almost directly towards us. Simulations show that in 2 billion years, the galaxies will sweep past each other. As they move apart, a ghostly bridge of stars and gas will connect them. Currently, Andromeda is a faint, fuzzy patch of light, barely visible to the naked eye. 4 billion years from now, Andromeda will loom large in the nighttime sky, for anyone on Earth who is here to see it. About 4.5 billion years from now, the galaxies will approach each other again, execute a few tight loops, and merge. Over the following billion years, they will settle into a smooth, large new galaxy. Milkomeda. It's a ship name. It's a couple name. Milkomeda. Oh, and there's a picture. Let me show you guys that. I could probably find a better picture online, actually. But this is the picture that's in the book. So this is a NASA image, like rendered by an artist, of what our night sky would look like after the merge. Oh no, this is after they've swept by each other and are approaching for a final time. So you can see that's our regular Milky Way galaxy, and then this would be Andromeda coming in. Can you see my cursor? There we go. This is the regular Milky Way, and this is Andromeda on her way over. Andromeda and the Milky Way forever, yes. They're in love. That's why they are approaching each other. This hypothetical new galaxy was named by Harvard University's Avi Loeb, who worked with Harvard postdoc T.J. Cox on computer simulations of the merger. They varied the assumptions and starting conditions, and each time it took 2 weeks on the equivalent of 20 state-of-the-art desktop computers. A collision between two galaxies isn't like a car crash. Galaxies are mostly empty space, so very few stars actually hit one another. At the position of the sun, if stars were the size of golf balls, they'd be separated by 1,000 kilometers. And even in the center of the galaxy, the separations would be 3 or 4 kilometers. Gravity will move stars around dramatically, but their solar systems will remain intact, so future Earthlings will be treated to a new night sky as we're wrenched from our routine orbit of the Milky Way disk into a new situation. What will happen to the Earth and the solar system in this galactic train wreck? There's a 10% chance that the sun will be flung into a tidal tail after the first close passage of the two galaxies. A tidal tail occurs when the gravity of two extended objects disturbs and distorts them. That would give us a bird's eye view of the subsequent action. There's even a 3% chance that Andromeda will steal the sun from the Milky Way. On the second and final approach, there's a 50% chance that the sun will move toward the dense inner region of Milkomeda, and a 50% chance that it will be cast out and our descendants will get to watch from afar as gravity blends the results of the collision into a smooth galaxy. All this is an entertaining sideshow. The main event is the encounter between the 4 million solar mass black hole in the Milky Way and the 50 times larger black hole in Andromeda. The black holes will converge near the center of Milkomeda, moving inward by transferring energy to stars they encounter, some of which will be ejected from Milkomeda entirely. This will take about 10 million years. When they approach within a light year of each other, they will enter a death spiral and release a paroxysm. Sorry, I'm just rereading that word multiple times because I've never heard it before. But they will release a paroxysm of gravitational waves before merging. I'm going to pause there for a second. Back to snakes really quick. Aniana Desai? Is that how you say your name? I can't tell where the breaks are. Because I don't think it's one full. And Aniana Desai? But they say, so basically they have these infrared sensors, snakes, so they can detect objects and organisms based on how much heat their bodies emit. So when you look at it, it's all like blue, green, red. Oh, that's strange. Ununya? Okay. Thank you for the clarification. Yeah, if I'm ever getting anyone's names wrong, please feel free to correct me. I'm terrible with that and like figuring out how to pronounce things. Obviously, you've seen me read this book. But yeah, that's not un. Umbrella. Okay. Unya. I think I got it that time. Umbrella U. Yes. But yeah, that's how snakes see. That's wild. Other animals, like, I want to know. There's probably ways to do this. I mean, science is the thing, but like, I want to go to a museum one day when COVID is over, or handled enough where we can go to museums again. And I want to go to like a science center or something, and I want to go into an exhibit, and I don't know if this exists, but tell me if it does, where they just have like an optics exhibit where they have like 15 different things where you can look into the little like viewfinder or whatever and see how like a snake sees, or like shrimp see, or like whatever. And I think that would be so cool, except also like if it's like just the shrimp thing where they see more colors, then I don't think that's possible, because like if they see more colors than us, then we just can't see the colors, right? And that upsets me deeply, because then I'll never know what color I am to the shrimp, you know? But that would be so cool, right? I want a museum to do that. If I was a museum curator, I would find someone who knew more about optics than me and have them make the exhibit. But I think that'd be really cool. All right. Fuchsia, magenta, yellow. It's one color. All right. I was right here. Okay. The merger between the Milky Way and Andromeda will not be unusual. Events like this are happening continuously in the universe. While the merger rate has declined as the universe expands, it's still significant. But not all mergers follow the pattern of black holes measured by LIGO. When binary stellar black holes merge and their spins happen to be counteraligned, the gravitational waves can carry away enough momentum that the merged pair experiences a recoil kick. The force of the kick can be enough to eject the merger remnant. Galaxies like the Milky Way occasionally spit black holes into intergalactic space. This can also happen to supermassive black holes after two galaxies merge. It's wonderful to imagine huge and naked black holes sailing through space between galaxies at millions of miles per hour. Half a dozen binary supermassive black holes have been identified. In the previous chapter, we saw that the LISA space interferometer is designed to detect the merger of such binaries. The theoretical tools required to model these mergers have only been developed recently. We won't have to wait billions of years for a signal, as we would with Milkomeda. The quasar PG 1302-102 is 3.5 billion light-years away. It has a binary black hole in a 5-year orbit, indicating that the black holes are only a light month apart. That means the death spiral is imminent. Although because of the time it takes the information to reach us, it actually happened 3.5 billion years ago. An even more exciting prospect is a pair of black holes 10 billion light-years away, each of which is several billion times the mass of the Sun. The orbital time of a year and a half means they're separated by 6 times the Schwarzschild radius, so the system is close enough to merging that it should be pouring out gravitational waves. These black holes actually merged billions of years ago, but we may only have to wait a few millennia to hear their space-time song. That's the end of that section. Chat is blowing up. Oh, how'd you guys end up here? You have no idea how you ended up here. That's why snakes stick their tongue out? So the sensors are in their tongues, I guess. I've heard that they like have to stick their tongues out to like see or sense things or something like that. That's crazy. I don't know how we started talking about snakes. I don't know how you guys got to this live stream. But yeah, I'm curious. How did you guys find Teach Astronomy? And if you've been here like for like before the Twitch channel started, tell me how you found the original. Because I know some people found us through YouTube, some people found us through Coursera with Professor Impey's streams, some people found us on Twitch. Hi, Absent Boy. How you doing? Hi, Pratik. You were looking for science tech streams, and this one seemed interesting because you have a little interesting coding. Yeah, I noticed that a lot of them. I always check the top page when we're streaming for Professor Impey streams, because usually those we get a lot more people than we do at on mine or me and Michael or Matthew streams. And the top 10 are usually coding streams and feeding ducks in a pond, or like feeding chickens on a farm. And they're interesting, but like I find them very funny that those are always the top ones. You found us through Coursera. Also, you like people reading to you. Well, you found a good channel then, because we do this every Monday. So we have other streams on Wednesdays and Fridays where we talk more about we do astronomy news on Wednesdays, and we do amateur astronomy on Fridays. So we just chit chat about that kind of stuff, and we'll have different subjects that we focus on and things. But Mondays are always reading. Esther Kiriani got here through Coursera. Oh, you found us through Coursera too. Maybe YouTube. Hi, Charlie. How you doing? You randomly clicked on a stream, Absent Boy. You found it through Coursera. Nice. Oh, it is Chris's birthday. Oh my God. Thank you for the reminder. I have to wish him a happy birthday. I have like 6 or 7 friends. And I mean, I guess Chris and I are friends. He's my boss, but I have like 6 or 7 friends that all have birthdays in these the last 2 weeks of January, and just trying to keep track of all of them is a lot. But yeah, that's really interesting. So it seems like several of you found us through Coursera. Some of you just found us through like a discovery page. That's cool. It's good to know. I'm glad you're all here. It means a lot. It really does. When I started this stream, I was like, nobody's going to come to this. But that's okay. I'll try. And now I have all these people that always hang out with me, and it's great. You like any astronomy knowledge? Yeah. Yeah, we're just trying to bring more like free and like fun and easily approachable astronomy education stuff to the internet, especially when people can't go to things like the museum with the cool optics that I said I wish existed and stuff like that. Oh, we did not talk about the Mars and Uranus conjunction. I didn't know there was a conjunction coming up. Did it happen already? Oh, thank you, Lynn Jersey. Thank you. I try. I feel like I missed something before. Oh, somebody asked, Ananya asked, astronomy as a career. Yes or no? What do y'all think? I think it's a good idea. It's not my career, personally. It's semi my career, kind of, now. But, yeah. Let Ananya know what you guys think about astronomy as a career, because I think it's great. Oh, the conjunction already happened? Okay. Yeah, I didn't even hear about that. I think it was because the what was it, Jupiter and... It was Jupiter and Saturn, right? In December? I feel like that one got all the... I don't know why it's so hard for me to say your name. I always get nervous. I'm so bad with names. I always worry that I'm gonna mispronounce them, and then I do because I'm overthinking things. I'm working on it. I'm gonna get back to reading though, because it's been a while. Okay. So the biggest black holes in the universe. Supermassive black holes bring to mind Gargantua, the dark centerpiece of the movie Interstellar. Gargantua is the destination of space travelers who hope to use a wormhole to vault across space-time. It's 100 million times the mass of the Sun. Its event horizon is the size of Earth's orbit, and it's spinning at 99% of the speed of light. As we've seen, Gargantua is the most realistic depiction of a black hole in popular media thanks to the input of Kip Thorne, who made sure the film did justice to both science and art. Gargantua is 25 times the mass of the black hole at the center of the Milky Way, but it's puny compared to the most massive black holes. The Sloan Digital Sky Survey located 10 black holes over 10 billion solar masses in the distant universe. They must have accreted material very rapidly to grow by a factor of 1,000,000 from their seed mass in only 1.5 billion years. These behemoths dwarf the size of the solar system. The record holder is a strong radio-emitting quasar with a black hole mass of 40 billion solar masses. And we have a figure for that as well, and that's the old one. There we go. So, this is the biggest black hole we have ever, well, it's potentially the most massive black hole ever found. NGC 1277 is 17 billion solar masses, although another study measured only 5 billion solar masses, but this is assuming the 17 billion solar masses. So this diagram shows the size of the event horizon in comparison to the solar system. So Earth's orbit is that tiny little dot in the center. Neptune's orbit is there, which is, if you don't count like Pluto and the Kuiper Belt, that's the edge of our solar system. And even if you do, it's like a little bit farther out. And this is the black hole's event horizon, which is massive. Just huge. So yeah, that's the biggest one we found, and it's so large. I think I see the it doesn't have much scope. Oh, what's in the cup? It's a matcha, it's a matcha tea. It's actually like a raspberry matcha. I used to work at a tea shop, and then the tea shop closed. And I got to take a bunch of the tea that we never sold home. So Oh, you got to get going. That's okay. Well, like I said, we archive all these streams, so it'll be here. The rest of the stream will be here for the rest of, for like the next 2 weeks. Oh, I'm glad you'll stick around. Yay. But yeah, the stream will be here for the next 2 weeks, and then after that, it'll be up on YouTube in the next like couple days, because Twitch erases things after 2 weeks. But yeah, you can always watch it back later, and then make sure to come back next week for the interview with an author, with Professor Impey. So that'll be fun. All right, let's see. Astronomers are cavalier about tossing around large numbers, so let's pause to digest the implications of extreme black holes. A black hole 40 billion times more massive than the Sun has a Schwarzschild radius of 4 light days, so the event horizon is 20 times the size of the solar system out to Pluto and the other dwarf planets. The black hole spins at a substantial fraction of the speed of light. Whereas the outer planets in our solar system take 250 years to complete an orbit, this much larger object spins once every 3 months. Although the mass of a small galaxy has been squeezed into a solar system volume, the mean density is 100 times less than the air you're breathing. The black hole emits no light, but the surrounding accretion disk glows brightly. A black hole of this mass is an active quasar phase. In an active quasar phase would emit 100 trillion times the luminosity of the Sun. What lies ahead for the most massive black holes in the universe? Galaxies grow by accreting gas from the voids of space and by mergers. Both of these paths for growth are diminishing. As the universe gets larger, the gas supply thins out and galaxies get more widely separated, so they merge less often. There's a correlation between stellar mass for a galaxy and its central black hole mass. It ranges from 10 to the 4th to 10 to the 5th solar mass black holes in globular clusters through 10 to the 6th to 10 to the 7th solar mass black holes in galaxies like the Milky Way, up to 10 to the 10th solar mass black holes in elliptical galaxies with 1 trillion solar masses of stars. There were so many power ofs there. Regardless of the size of the stellar system, the central black hole is about 1% of the total mass in stars, and it's only 0.1% of the mass of the galaxy when dark matter is included. I've spent years trying to understand the life and times of supermassive black holes. My student John Trump and I racked up dozens of nights on 6.5 meter telescopes in Arizona and Chile. Modern instrumentation means data that once took a lifetime to gather can be gathered in the time it takes for a graduate student to finish a thesis. With classical spectroscopy, the light from one active galaxy passes through a slit and gets spread into a spectrum. The instrument we were using in Chile placed little slits on hundreds of targets over an area of sky the size of a full moon. A single long exposure might yield 100 black hole masses. With this data, we hope to tell the story of the rise and fall of quasar activity in the universe. Quasars are so far away, but it makes no difference which direction you point the telescope. But I'm partial to the southern sky. The Milky Way arching overhead like a ragged silver curtain is spectacular, and there's the bonus of our neighbor galaxies, the Magellanic Clouds, suspended like cotton wool balls on black cloth. It was so dark outside, I could read a book by starlight. We gathered statistics that traced the overall arc of black hole evolution over cosmic time. To do this meant sampling all the black holes, not just the extreme ones. I'd got over my youthful obsession with blazars and now wanted to know what controlled the overall population of active galaxies. By analogy, if you want to know the population of cars, you'll be counting a lot more Fords and Toyotas than Ferraris and Aston Martins. One big mystery was the fact that black holes are only active a small percentage of the time. Another is the tight relationship between the mass of the central black hole of a galaxy and the mass of all the old stars in the galaxy, which are distributed on much larger scales. It's as if the black hole knows what kind of galaxy it lives in. Just going to pause there for a second. I saw some things in the chat. Oh, I think they left already, but yes, next Monday. Next Monday we're doing the author chat. You would love to work on SpaceX one day? Yeah. SpaceX is, that and like the you know, the big various country government space like NASA, ESO, ISRA, I think it is. The Indian space program is ISRA. But those are like the big ones, you know. Sometimes you think life is a simulation, like you don't get to do what you want, but time goes on forever. ISRO, okay. Yeah, but like those are, you know, those are the big ones, you know. If you get to work on one of those, like that would be, and SpaceX, that's the dream, right? That's the big one. It's like for me, I'm my like actual thing that I went to school for and stuff was film and television, which is why I'm the resident Twitch expert, as I call myself, for the TeachAstronomy team. And you know, the dream is to work for like Disney or CBS, Viacom, with like Nickelodeon or something like that, you know. The Rocket Lab seems cool. Yeah. Yeah, good for you guys. Hell yeah. Chase those dreams and work at SpaceX. That would be so cool. And then call me up and let me interview you about working at SpaceX or NASA. Because that would be awesome. All right. Apologies if you guys hear a hum in the background. Somebody is doing some landscaping outside my window. Oh, a planetary geologist would be really cool. We actually got to work with someone who does, it's a little different, but planetary like seismology and stuff. And like researching like how plate tectonics work if they exist on different planets, and like she's part of the team that sent InSight up onto Mars, which unfortunately InSight's not able to do their like digging thing, which was the plan, but still really cool stuff. A bunch of research about how like plates like the tectonic systems and the seismic activity on different planets. You saw an interesting video on YouTube yesterday? Yeah, send me the link. I'll check it out later. I will give that a look. All right. I'm going to get back to this. Okay. We gathered statistics that trace the overall arc of black hole evolution over cosmic time. To do this meant sampling all the black holes, not just the extreme ones. I'd got over my youthful obsession with blazars and now wanted to know what controlled the overall population of active galaxies. By analogy, if you want... Oh, did I read this already? I guess so. Sorry. I totally did. Yeah, okay. Whoops. I think. I'm forgetting what I read now. That's not good. It's one of those days. Whew. Okay. In our data, the biggest black holes grew quickly in the first few billion years after the Big Bang, and then were starved of fuel. The more numerous smaller ones grew slowly until, in the past 5 billion years, they too became mostly quiet. The peak of the quasar era is long over, but black holes don't disappear. So presumably they're being starved, with less fuel to power them as time goes by. That makes sense because the expanding universe is getting less dense, and the rate of galaxy collisions is declining. But for any particular epoch in cosmic time, and any particular galaxy mass, we cannot predict which black hole will be booming and which will be silent. It's equally hard to predict the future of these quasars. We made the research into a game, laying out the quasars as cards on a table, like stamp collectors. Were some of them bright because they had a companion galaxy to feed on? In a few cases, but not always. Were some dim because they lived in a gas-poor galaxy? Not necessarily. We couldn't identify any trigger for nuclear activity. The overall painting made sense, but the individual dots of paint could be any color of the rainbow. Nature is creative. It makes black holes that span a factor of 1 billion in mass. In our work, we've never found a black hole more than 10 billion times the sun's mass. That's a little disappointing. I always wanted to claim that on my CV. Theorists predicted a limit on black hole mass 10 times larger, about 10 to the 11 solar masses. At that level, accretion physics becomes important, regardless of the host galaxy's mass. It seems to be nature's limit on black holes. To grow even bigger, the black hole would have to accrete 1,000 solar masses per year, and that much gas would collapse into new stars on scales of hundreds of light years, well before reaching the black hole. Also, the black hole starts to self-regulate. Radiation flooding out pushes away the incoming gas and stops further feeding. The bloated beast is grasping for food, but there's none within reach. That's the end of that section. And there is also a figure to go along with that, talking about the different black hole, like the size of black holes. So we have, it's just a simple chart of observed mass ranges of compact objects. So the objects that we've found that are the most massive. So we've got the supermassive black holes going well above a million solar masses, and it goes up higher to billion solar masses. The intermediate mass black holes are around here, between about 100 and a million solar masses. Stellar black holes are, looks like around 5 to 100 solar masses. And then you get the neutron stars and the white dwarfs. So yeah. Oh, hi Parzival, how you doing? I'm doing all right. Reading the last chapter. It's very exciting. I am excited to, I very much enjoyed reading this book, but I'm also excited to find out what's the next book we're going to read, because I like reading books, you know? It's a good time. All right. The era of stellar corpses. Even though the massive black holes at the centers of galaxies are approaching a natural limit, the death of massive stars continues to lead to more low-mass black holes. Stellar evolution is a battle between the forces of light and darkness. Energy from nuclear fusion keeps the star puffed up while gravity tries to make it shrink. As we've seen, these forces will be balanced in the sun for another 5 billion years. Then gravity will win and crush the core into a white dwarf. Massive stars evolve more quickly, and when gravity wins, they'll leave behind neutron stars or black holes. The universe is heading for darkness. The first star formed about 100 million years after the Big Bang, when the universe was 30 times smaller and hotter than it is now. Galaxy assembly and star formation peaked about 3 billion years after the Big Bang, and they've been declining ever since. Stars are currently being formed at a 30th of their peak rate, and the decline will continue as less and less gas is available to form new stars. Even if we waited forever, only 5% more stars would form than have been formed up to this point. These are averages. At any epoch, more massive and gas-rich galaxies have higher star formation rates than less massive and gas-poor galaxies. The diminishing supply of gas will be eked out for a long time by stars that eject some of their mass late in life or die as supernovae. Along with the declining rate of new stars forming, an increasing fraction of the stellar mass in all galaxies will be in the form of collapsed remnants. Getting tongue-tied. Once star formation finally ceases and the last black hole forms, roughly 100 trillion years from now, gravity will have its final victory. By coincidence, this is the life expectancy of the lowest mass red dwarfs, which are cool stars just above the mass sufficient to maintain fusion, 0.08 solar masses. The timescale is enormous. We're still in the very first phase of the universe as illuminated by stars, the equivalent of a baby, only a week old. In this distant future, as the stellar era extends, in the distant future as the stellar era ends, the 400 billion stars of Andromeda will be equally divided between white dwarfs and brown dwarfs, with a small residue of neutron stars and black holes. Stars above 0.08 solar masses and below about 8 solar masses will collapse to roughly the size of the Earth and radiate their remaining energy into space as white dwarfs. Failed stars ranging from 0.08 solar mass down to 0.01 solar mass, so from 10 to 80 Jupiter masses, will collapse into brown dwarfs, perhaps feebly fusing hydrogen into lithium. Neutron stars will be 0.3% of the total stellar remnants in Milkomeda, and black holes will be a paltry 0.03%. As the eons pass, the white dwarfs and brown dwarfs will cool such that their radiation shifts to invisible infrared wavelengths. For a while, black holes and binary systems will be bright due to gas siphoned from their companions. But eventually, the companions will also become stellar corpses, and that source of gas will be exhausted. Galaxies will then slowly fade to black. That's the end of that section. We're just going to pause real quick. Looks like we're doing pretty good on time. We have, for context, we've got about 8 more pages. Like 7. The last page is like a paragraph. I love this too because I was so surprised that we were in the last chapter, because this is where I am in the book. And I was like, there has to be at least like 2 more chapters, right? There's a lot. No. These are notes and citations. Just all of that, which is crazy. Which makes sense. Oh, and there's an index as well. So citations and an index. But like, I forget that like you need to include that stuff in nonfiction books because, like I said, I don't read them very often. So I was like, oh, there's not that much left, actually. All right. A future of evaporation and decay. The far future we've just described applies not only to Milkomeda, but to each of the hundreds of billions of galaxies in the observable universe. Their stars are subject to the same laws of astrophysics as stars in our system. But our descendants will never get to see all the other galaxies go dark. The reason is dark energy. Dark energy is the biggest enigma in cosmology. Astronomers discovered in 1995 that the universal expansion is accelerating due to something that works in opposition to the force of gravity, which should cause deceleration. The cosmic pie is 25% dark matter, 70% dark energy, and 5% normal matter. Black holes large and small make up 0.005% of the universe, so they're a very minor component. Dark energy means that galaxies we can see now will steadily be removed from view because they'll be receding faster than the speed of light. In 100 billion years, or 10 times the age of the universe to this point, all galaxies beyond Milkomeda will have exited our event horizon. We'll be reduced to starting at our navel, metaphorically speaking. The end of the stellar era and subsequent events will only be measured in the galaxy we inhabit now. After Milkomeda goes dark, the future is evaporation and decay. Over time, stars within a galaxy exchange energy, with lighter stars tending to gain energy and heavier stars tending to lose energy. Recall the analogy of a bowl containing black marbles and wooden balls the same size, where, if it's shaken, marbles migrate to the bottom of the bowl. Some stars will gain enough energy to leave Milkomeda, leaving the galaxy smaller and denser. This increases the interaction rate between stars, so the process accelerates. At the same time, the decay of stellar orbits caused by the emission of gravitational radiation will move stars inward. After about 10 to the 19 years, 90% of the stellar remnants will have been ejected. Milkomeda will evaporate, with the remaining 10% of their remnants falling into the supermassive black hole. After the merger of the Milky Way with Andromeda, the central black hole will be about 200 million times the mass of the Sun. It will eventually grow to about 10 billion solar masses. If the age of the universe to this point were the first week of your life, you would need to live another 10 million years to watch this play out. Thereafter, the distant future gets hazy and speculative. Physicists venture beyond the standard model of particle physics to explain why the universe contains far more matter than antimatter, and to try and unify the electromagnetic force with the weak and strong nuclear forces. These schemes are called Grand Unified Theories, GUTS, G-U-Ts, I guess, and most of them predict photon decay. If photons decay, normal matter is not stable. Proton decay has never been observed, and the current limit is 10 to the 34 years, which rules out some but not all grand unified theories. If protons decay, all stellar remnants except black holes will disintegrate into electrons, neutrinos, and photons. The final dissolution of the universe takes a staggering amount of time. Assuming that normal matter decays, only stellar and supermassive black holes will remain. Stephen Hawking predicted that black holes emit a feeble amount of low-energy radiation that causes them to slowly evaporate. It's important to recognize that this is speculation, as Hawking radiation has never been observed, and no technology to detect it yet exists. The timescale for massive star remnants to evaporate is 10 to the 76 years. The supermassive black hole at the center of Andromeda will evaporate in 10 to the 100 years. Everyday analogies fail miserably to convey this level of near eternity. Even this is just a way station on the path to terminal heat death for the universe. And we have a figure for this very cheery topic about the terminal heat death of the universe. Here it is. So this is this is the far future timeline of the universe. So on this logarithmic chart, the entire history of the universe up to this point is at the far left. Even the disappearance by evaporation of the most massive black holes is not the last physical process. After yet another vast interval, normal matter decays and the universe is left as a high entropy soup of particles and low energy photons. So we start here with our Big Bang. This is the primordial era, which is, I believe, this is the whole thing that we're in right now. Then the saliferous era, the degenerate era, the black hole era, and the dark era. So this is 1 second. Oh, I understand. Okay. Logarithmic, yes. Okay. Yes, this is like 1 second. So it's saying that the primordial era was mostly like a bunch of stuff happened very quickly. So that was 1 second in the universe. Then this is when the first star began to shine, that first bar there. The second one is 13.8 billion years, the present day. So that's from 1 second of the universe to where we are now, that little itty bitty. And then this is where the last star dies, and this is when the last supermassive black hole evaporates. And then just heat death. Yeah, the terminal heat death of the universe doesn't sound like a good time. And honestly, I'm okay with not being around for it. Doesn't sound great. Not a fun party, you know? All right. This is in quotes. Things fall apart. The center cannot hold. Mere anarchy is loosed upon the world. So wrote William Butler Yeats in 1919. He was commenting on World War I, but he might have been anticipating the end of the universe. The scientific context for this outcome is the second law of thermodynamics, the universal tendency to increasing entropy and disorder. Arthur Eddington confirmed general relativity, but didn't believe in its prediction of black holes. However, on the inevitability of heat death, he was unequivocal. He wrote, quote, "The law that entropy always increases holds, I think, the supreme position among the laws of nature." If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. End quote. That's edgy. Wow. Sick burn. Black holes are enigmatic, so it's appropriate that they will be the last objects remaining at the end of the universe. That's the end of that section, but I will continue. in just a moment. Okay. Living with black holes. Oh, what was his name? The guy that did that quote, that was Arthur Eddington. Yeah, that was Arthur Eddington talking about the inevitability of the heat death of the universe. Living with black holes. Our narrative has become dark and gloomy. Don't forget that the universe is built for life. Although astronomers haven't found any examples of biology beyond the Earth, they're optimistic that they will. In the solar system, there are potentially habitable locations on Mars, Europa, and Titan, and on a dozen giant planet moons where water exists under a crust of rock and ice. In 1995, the first exoplanet, or planet orbiting another star, was discovered after decades of fruitless searching. Since then, the floodgates have opened, and the current census of confirmed exoplanets stands at over 3,700. That number's like a lot higher now, I think. We can look at that in a minute. Who hurt you, Arthur Eddington? Oh my gosh. Anyway, the early exoplanets were discovered using the Doppler method, which revealed them because of the way they tugged on their parent star. More recently, most discoveries have used the transit method, where the exoplanet eclipses and momentarily dims its parent star. The Milky Way contains a staggering 10 billion terrestrial planets with surface conditions suitable for liquid water. Most of the 100 billion stars in the Milky Way have terrestrial planets. If life requires only carbon material, liquid water, and a local source of energy, there may be several 100 billion habitable locations on moons and planets where the surface is less hospitable. The real estate of time is as important as the real estate of space. There was enough carbon in the universe for the Earth's clone to form within a billion years of the Big Bang. So some terrestrial planets... Oh, gosh. I'm going to start that sentence over. There was enough carbon in the universe for an Earth clone to form within a billion years of the Big Bang. So some terrestrial planets have an evolutionary head start of up to 8 billion years on the Earth. Our ignorance is simply too great to imagine all the forms of biology that might evolve on these myriad worlds. Given that we don't even know of the life on one other world, it might seem presumptuous to ask about the prospects of life far into the future. But let's do it anyway. Life doesn't need a star. It simply requires an energy source. According to the second law of thermodynamics, biology needs a temperature difference to provide a usable source of energy. Life on Earth exploits the temperature difference between the sun and the cold vacuum of space. The Earth absorbs photons from the sun at 6,000 Kelvin and emits 20 times more photons at 300 Kelvin into the sky. Biological organisms run complex processes that lower the entropy or disorder locally, but those organisms emit heat or waste energy that's eventually radiated into space. The energy argument applies even if life becomes computational, in the sense of AI, rather than biological, because any manipulation of information requires some form of energy. As the stars in the universe exhaust their nuclear fuel, a hypothetical civilization of the far future could still exploit the temperature difference between cooling embers, white dwarfs and brown dwarfs, and deep space. The physicist Freeman Dyson considered the future of life and concluded that biology could be sustained in an era of diminishing returns by hibernating for increasingly long spans. That will work for 10 billion years or so, but what about when all the stars fade to black? Salvation may come from black holes. Energy could potentially be extracted from a black hole spin. Just beyond the event horizon is a region called the Ergosphere. The word comes from the Greek for work, and it was coined, no surprise here, by John Wheeler. The Ergosphere is dragged around by a spinning black hole like water is dragged around by a whirlpool, and it's thinner at the black hole's poles. Think of a spinning balloon filled with water where rotation causes it to bulge at the equator. Roger Penrose proposed in 1969 that it was possible to extract energy from the ergosphere. With the right trajectory, an object can enter the ergosphere and leave with more energy than it had on the way in. The black hole will spin very slightly slower as a result. A civilization could do careful calculations, toss things into a black hole, and harvest the extra energy they have when they're ejected again. Another clever idea is to flip the temperatures around and have a cold star in a hot sky. Black holes in the present universe are often bright because matter falls towards them and forms a hot accretion disk. However, in the far future, the gas will have been consumed and black holes will be cold and dark, except for a feeble drizzle of Hawking radiation with a temperature of a fraction of a degree. Compared to that, the universe has a balmy temperature of 2.7 Kelvin due to radiation left over from the Big Bang, a temperature that will decline as the universe continues to expand. Theorists calculate that an Earth-like planet orbiting a black hole close enough that it appears the same size as the sun in our sky could extract about a kilowatt from the temperature difference. It's probably enough to sustain a miniature or very efficient civilization. And we have a figure. Somebody said Dyson's in the house. All right, so this it's a very basic figure. Hold on. Oh my gosh, I can't flip the page. Jesus. Oh my gosh. Okay. So this says, a method for a far future civilization to extract a small amount of energy from a black hole. In a conventional Dyson sphere, a shell built around a star captures energy from the star and radiates waste heat outside. But in this version, Hawking radiation from the black hole is colder than the microwave radiation from the Big Bang, so the shell absorbs microwave radiation from the outside and radiates waste heat to the black hole, leaving a little energy to be harvested. It does look like a pupil. That's really funny. It even has like the arrows on the inside feel like the little lines, like if you look at a pupil really closely, like you see the little lines. There's probably, I guess those are veins. That probably makes more sense than just the little lines. Let me know if you can see and hear me, all right? That was a process. Oh my God. I'm so sorry. So if you're new here, we've had that issue once or twice before where for some reason when I open the PowerPoint, it just kills my stream when I try to switch it back. And I thought I had fixed it. And I guess I haven't, but it hadn't happened in like a month, so I thought it had been fixed. So I used this program called Streamlabs, and it's like a middleman between me and Twitch, so then I'm able to like have different setups, and that's how I switch between like the stream setting up and like this camera, or like when I have Matthew or Michael and I have them in a little thing. And sometimes it just crashes, and so like it crashed, and then this time I was like, okay, I'll just it's happened before, we'll fix it, and like we had to go live, you know. Also, I'm just gonna say in the chat, if you can't see me, try refreshing your page. I think I'm back. But like I normally I'm able to just close the program, the Streamlabs program, and then turn it back on and start the stream again, but it wouldn't even reopen. So I had to totally reset the computer, and then it wouldn't recognize my camera and my mic, so I had to unplug those and like plug them back in. And it was just for some reason it just hates PowerPoint, but it's just a window. It's just looking at a window. So I don't even know what. I don't know. I'm going to talk to my friend and our resident computer programmer, Alexander, about this in the future, because I don't want this happening anymore. It's very frustrating. But hopefully everyone is back, and we will continue. So I think I left off. Where did I leave off? Oh, yeah. Okay. Sometimes technology helps and sucks. Yeah. All right. Well, back to reading. We were so close, too. There's like 3 pages left in the whole book. All right, at least there's no more figures, so it's not going to happen again. All right, hopefully everyone's back. A similar strategy was used in the film Interstellar, in which a world called Miller's Planet orbits close to the massive spinning black hole Gargantua. Gravity slows down time so much that during 1 hour on the planet, 7 years pass off-world. In this scenario, the inhabitants of Miller's Planet can generate 130 gigawatts of power, but the film is off the mark in imagining people could live there. Such a large amount of energy heats the planet to 900 degrees Celsius, enough to melt metal. The problem with using black holes as a means to draw energy from Big Bang radiation is the speed of the cosmic expansion. The temperature of that radiation is 2.7 Kelvin now, but as dark energy causes the universe to grow exponentially, those photons are stretched by the expansion to have very long wavelength and low energy. Within 100 billion years, the Big Bang radiation will have a temperature that's a tiny fraction of a degree. Civilizations will have to switch strategies. The Hawking radiation for a minimum mass black hole 3 times the mass of the Sun has a temperature of 2 times 10 to the negative 8 Kelvin, and a luminosity of 10 to the negative 29 watts. That's truly feeble, but apart from black hole spin, it will be the only energy available until these black holes evaporate after 10 to the 76 years. To capture all the radiation, a civilization would have to surround the black hole with the kind of sphere Freeman Dyson imagined intelligent aliens might use. Then attention will turn to the massive black hole at the center of Milkomeda. With a temperature of 6 times 10 to the negative 18 Kelvin and a luminosity of 10 to the negative 48 watts. It's a feeble fire at which to imagine warming one's hands. Living in the far future will require parsimony and patience. But until that last black hole evaporates after 10 to the 100 years, time is one thing in the universe that will never be in short supply. I have glimpsed black holes in my research. They are massive and inscrutable, seen across the gulfs of space to distant galaxies. My span will be short compared to theirs. How long will they endure? Blink quickly. You have done that a billion times since the Big Bang. The time until the most massive black holes dissipate is to the age of the universe, as the age of the universe is to a blink of an eye. And so on, 3 times more times, to reach 10 to the 100 years. Hi, I keep seeing people coming back in the chat. Yeah, we've returned. I'm sorry, it's such a technology, man. But I'm glad you guys were able to make it back. All right. This much time is unfathomable. The word clock is quaint. It comes from the Middle English word for bell, a reminder of a time when clocks had no hands and no numbers because so few people could read. Long after human time, after pendulum clocks, after the mechanical time of Timex and Rolex, after the last radioactive atoms have decayed, and after the last pulsar has spun down, there will be black hole time. I imagine I'm immortal. If I could watch until the end of black hole time and see what we or civilizations from other stars have done, what would I see? First, there is a barbaric age, an extension of the one we live in, when civilizations rage against one another and the worst fate for a vanquished foe is to be flung into a black hole and suffer the torments of being torn asunder by gravity. Then perhaps the civilized age, when creatures leave images frozen onto the event horizons of large black holes as timeless memorials. As an optimist, I imagine an age of knowledge, when some learn how to read the information stored holographically on the event horizon, and others venture into spinning black holes to take refuge on the time-like surface, a hall of temporal mirrors where you can travel back and forth to meet your past and future self, but never leave. Finally, an age of sentience, when life is distilled into pure computation and black holes are a form of information storage. How pleasing to think that these ciphers might sustain the heartbeat of the universe. If I could flip the page, we could finish the book. Okay. Gravity is the weakest force, but it's the most grandiloquent and the most persistent. The other forces have long since quit. Subatomic particles have all decayed, and electromagnetic radiation has been diluted and stretched into oblivion. All the crashing chords of gravitational radiation as black holes merge are in the past. The only music of the spheres is the low thrum of black holes spinning. Slowly, inexorably, they evaporate. This is the end. The universe has dissipated to an almost perfect smoothness, with the vacuum lightly ruffled by quantum fluctuations. And that's it. That is the end of Einstein's monsters. Yay! We did it! With only a short pause to reset my computer and start the stream over. But yay! That is Einstein's monsters. Thank you guys so much for being here with me, for reading through that whole book. It was dense at times. It was so super interesting most of the time. It was fun to hear Chris's anecdotes and analogies. I enjoyed it. Did you guys have a favorite part? Tell me, what was your favorite part? The dark area was the end of Einstein's monsters. Yeah. Chris likes to be grandiose in those things, right? He has to end it with the heat death of the universe and the yeah. It was interesting. I liked it. You expected more. Yeah. That was fun. Well, before we go, while you guys, if you guys want to chat about some of your favorite parts or whatever, or like some of the things that the book left you with, feel free. We can talk about that. You liked anything about black holes? Nice. I am going to start a poll. Actually, before I do that, I'm going to pull up a list of the other possible books that we can read next. That got so bright. Oh my gosh. Okay, so like I promised, I wanted to ask you guys, because you guys are the ones that are here every week, what book we should read next. So I'm going to give you a little short description of the other books that we could do. When is the next stream? It's going to be next Monday for book stream, at least. We're doing our regular Wednesday and Friday this week. So if you're talking about any stream, it'll be Wednesday. But oh, thank you for the anonymous cheerer. Charlie, you said if I'm voting, you'd give your vote to me. Oh, you mean like you don't want to choose? Oh, well, I mean, I'll read anything. I want you guys to vote. You know, I'll vote a little bit, but I'm down to read any of these. Honestly, I'm very excited. Oh, thank you, Charlie. But yeah, so there's a few different books. Also, if you're newer here, we are specifically looking at Professor Impey's books just because we have access to Professor Impey, and we can be like, yeah, we can read those. Yes, no copyright issues, and he could say yes. So unfortunately, we're focusing just on his books right now. I mean, not unfortunately, they're very good books, but we can't go outside of books that he hasn't written, just because, we can't guarantee that they are okay with it, because we don't personally know, like, Kip Thorne or like the Stephen Hawking estate. We can't get in touch with them. Maybe one day that would be really cool. But yeah, so I'm gonna give you guys a quick description of the other books, and I'll actually first I'm going to link you guys. So this is Professor Impey's website where he lists his books. So if you guys want to click on that, you can see the ones that I'm talking about and read a little bit more about them. So also I think there's one or two missing, so I'll have to find those as well, because I don't think we've updated this page in a while. But we have Humble Before the Void, which is a book about This is very different from from his regular books and from like Einstein's Monsters. It's more of I wouldn't say a memoir, but kind of a memoir. It's about his trip to Tibet, I believe, because he visited Tibetan monks. Yeah. And he went for for this like conference with Tibetan monks and the Dalai Lama, and the Dalai Lama actually does a what's it called? Has a little forward in the book, which is really cool. But he talks about that trip and teaching, astronomy to these Tibetan monks and hearing about how they feel about astronomy mixed with their religion and stuff like that. So it's much more of a like a memoir-y, I guess, kind of thing, or it's about this trip that he took. Then there's Shadow World. That is his only novel, his first and only novel, and it is about I'll read it here, I guess. Shadow World inhabits the boundary between narrative fiction and science fiction. It explores the tension between artifacts and natural forms, between reality and illusion, between the science that is and the science that might be. It's kind of it's about a Scotsman like himself that is fleeing family secrets and is like on this adventure to different parts of the world. So it seems interesting. And then there's he wrote this one with somebody else, so I'd have to clear this with Holly Henry, but I probably could. There's Dreams of Other Worlds, the amazing story of unmanned space exploration. So that is about unmanned space exploration. I'm going to skip Frontiers of Astrobiology because he edited that one. There's a few on this page where he just edited them. So they're like collections of essays or something. So again, it's like I would have to clear it with all these people. And then there's Encountering Life in the Universe, Ethical Foundations and Social Implications of Astrobiology. So this one examines the intersection of scientific research and society to further explore the ethics of how to behave in a universe where much is unknown. Taking contributions from notable experts in several fields. This is also one where he edits it. Damn, that sounds really interesting. But we'll wait on that one because I think I could do those. I just need more time to prep them because I'd have to talk to everybody. Scientists are usually chill about that kind of stuff, but we're also going to skip talking about life, but we will come back to this one day. And then there's The Living Cosmos, Our Search for Life in the Universe. So Chris leads the reader through the history from the Copernican Revolution to the emergence of the field of astrobiology, the study of life in the cosmos. So yeah, this one kind of talks about this says, written in non-technical language, this book is ideal for anyone wanting to know more about astrobiology and how it is changing our views of life and the universe. Parzival is on it with those links. And then we have the duo of how, and we don't have to read these in sequence, but we have How It Began, A Time Traveler's Guide to the Universe, and then How It Ends, From You to the Universe. So How It Began is a majestic account of the most fascinating phenomena in our universe and the science behind them. So Chris guides us through space and time, leading us from the familiar sights of the night sky to the dazzlingly strange aftermath of the Big Bang. And then in How It Ends, it is about the fascinating science behind the eventual end to everything, from the individual to all existence. So that one... it says, with a healthy dose of humor, How It Ends illuminates everything from the technologies of human life extension and the evolutionary arms race between microbes and men, to the inescapable dimming of the sun and the ultimate Big Rip. So that's going to get a little more existential if we do that one. But I would like to, if we picked one of those, I'd like to do how it began first, because, it makes sense. And I have a feeling I'm missing one. Does he list them in this book? Because Einstein's monsters isn't listed here. Oh, maybe that's everything, actually. What is Beyond? There's a book listed here that's called Beyond, and I've never heard of... Let me look up Beyond by Prof Impey. Oh, I know what Beyond is. Okay. Beyond is the book that he wrote before Einstein's Monsters. So it says... It's a nonfiction book by Chris that discusses the history of space travel and the future trajectory of human exploration of space. Cool. So it's he's got the one about where'd it go? Dreams of Other Worlds is about unmanned space exploration. Beyond is about manned space exploration. So there's a lot of info there. But I am going to make a little poll for those of you who have stuck around. So I appreciate you. Let me do that. I want a new poll. Okay. What book should we read next? Question mark. All right. I'm going to list all of these. How it began. Oh, gosh. Beyond. These are in no particular order. Dreams of Other Worlds. Oh my gosh, typing. Just gonna use this to get all the names instead of flipping between these tabs. Okay. Oh, Shadow World. I almost forgot. 1, 2, 3, 4, 5. Can I add another one? Oh no. It only lets me do 5 options. That's so annoying. Okay. It didn't seem like anyone wanted to read Shadow World, so I'm gonna skip that one for now because I think you guys all tend to gravitate to unless. Okay, you know what? This is how we'll do it. I'm gonna not put Shadow World on there, so I can fit everything else. Yeah, and I'm skipping how it ends because I don't want to read that before how it begins. And I will give it a 5-minute duration. And I will start the poll. And if you want to... so that should be, if you guys are on, whatever you guys are on, it should be in the upper... It should be on the top area of the chat, whatever you guys are looking at, I think. So you guys can vote in that for the next 5 minutes. And if you want to vote for the novel, Shadow World, just type that in the chat. But don't vote for Shadow World and also for something else. Try to vote only once. If you vote multiple times, that'll be very confusing. I hope you can't do that. What should I vote for? Interesting. Well, I have Humble Before the Void on my shelf, which is like tempting. But then part of me is like, well, but if I don't have the book that we decide on, then Matthew and Chris will have to give me another book, which means that I have more books to put on my bookshelf, and that's very exciting. I always like putting more books on my bookshelf. It looks like people are in between Dreams of Other Worlds and Humble Before the Void. We got 4 for Dreams of Other Worlds. I That one does sound interesting too. Man. Oh, now we've got one for the living cosmos. Interesting. I don't know. Part of me wants to read Beyond. I'm also a big fan of I think I'm in between Beyond and Dreams of Other Worlds because I really like space travel stuff. I think that's really interesting. Somebody voted for Beyond. Thanks. But yeah, I'll let you guys do that. What else? I can do my housekeeping stuff early while we do this. Just a reminder that we're Twitch affiliates. You guys all know this already, but I'll say it anyway. I guess there's a couple new people. But we're Twitch affiliates, and that means you're able to do the bit cheering thing like Anonymous Cheer did, and you can also subscribe to us. If you subscribe, you get access to a cute little emote or multiple. If you do the higher level subscriptions, you also will get access to our subscriber only Discord channel. Also, I should put the link to the Discord in general in here as well, because we have new people and we have a Discord and it's fun. There's more than 1,000 people. I think we're at 1,200 now that are on the Discord, always talking about science stuff and astronomy stuff, which is really cool. So I'm gonna share that. Where is that? Can I share this, please? No. Am I in streamer mode? Yes, I'm in streamer mode. How can I share the... You know what? I'm gonna do it this way instead. Astronomy. I'm gonna pull it from an astronomy state-of-the-art video because that's easier. There we go. But yes, if you guys want to chit chat with each other and with a bunch of other cool people, you can do that right there. And yeah, we have a little subscriber only channel on there that I'd add you to if you subscribed. And yeah, and if not, if you can't do the subscription thing, that's totally fine. If you haven't yet, please follow us. Then you will get notifications for when we go live, and it really helps out the channel. The more followers, the more I think Twitch will recommend us. I don't really know how that works. What did you send me? ET signal from Proxima Centauri, a conversation with Breakthrough Initiative's Pete Warden. Ooh. Very interesting. So that link that Turbop Slayer Parzival sent is an article about the Breakthrough Listen project. That sounds interesting. Very cool. Okay. So they said they got a signal that was probably interference, but it's the first signal that passed their basic test, they said, for a radio telescope in Australia, which is very exciting. Yeah. Cool stuff. Oh, for Wednesday, can we discuss the recent conjunction? Yeah, I can totally, we can write that down. Oh, the poll is over. I didn't even vote. It's okay. But it wouldn't have changed anything. So it looks like we are going to be doing Dreams of Other Worlds. Very exciting. Cool. I hope everyone is happy with that. And it looks like Humble Before the Void and The Living Cosmos came in second, tied. And Beyond was third, or fourth, I guess. So, I mean, we'll definitely, I don't think I'm going anywhere for a long time. I'm looking for jobs and stuff, but I could totally do this outside of a job as well. It's only a couple hours a week, so it's fun. You can have the links and download them. Oh yeah. Yeah, if you guys want Parzival, I do not know where he gets them, but he has links to a lot of these, to the PDFs of a lot of these books, and any book that you want ever, I think. So you guys can use those links if you want to get a book that is free, because I know not everyone can afford. Did it freeze again? No. Okay. Sorry. I got scared. But yeah, so I think that's pretty much it for today. I'm excited. I hope everyone is happy with that result. So Dreams of Other Worlds, that'll be fun. That's the one that's all about unmanned space travel. So. Oh, you said I saw the nope, and I was like, "Oh, are you not happy with the results?" Because it came in right after I said, "I hope everyone's happy with the results." I think you meant to say nope to "Did I freeze?" So, I hope that's what you meant. But yeah. So I guess I will see you guys next week. Be sure to prep your questions for Chris. I mean, you don't have to prep anything. But be sure to be here, and I'm pretty sure we'll do the same time, 10 a.m. If not, well, it's 10 a.m. for me. The same time we normally start, it should be. If it's not that, it'll be like an hour later, so it'll be like the second half of what we normally do. But that will be on the schedule